Welcome everyone. In this video, we are going to walk you through the process of normalizing Spotify-style music streaming app database into third normal form. First, let's start with the business rules that guide our database design. A user can have multiple playlists. A playlist can include multiple songs. Each song is by one artist but may belong to multiple genres. The same song can appear in different playlists. Playback history is tied to user, timestamp, and song. And lastly, artist and genre details should not be duplicated. With these rules in mind, let's take a look at the first normal form table overview. In this table, all the information such as users, playlists, song, and playback history is in a single table. This design still has redundancies. To address this, we move to the second normal form. Here, we break the large table into smaller ones. Users table stores user details like user ID, username, and email. Playlist table contains playlist ID, playlist name, and playlist created date with user ID as a foreign key. Songs table manages song information, including song ID, album ID, artist ID, and genre information. Playlist song table resolves the many-to-many relationship between songs and playlists, and playback history table tracks user activity with details such as user ID, song ID, stream date, and like status. This setup removes partial dependencies, but some problem remains.
Now let's move into third normal form. Here are the requirements for third normal form. The first one is that it must be in second normal form, and there should be no transitive dependency. Now, what exactly is transitive dependency? Transitive dependency happens in a table when a non-key attribute depends on another non-key attribute instead of depending directly on the table's primary key. Here we have a simple diagram. As we can see here, non-key attribute A depends on non-key attribute B, and non-key attribute B depends on the key attribute C, which makes non-key attribute A a transitive dependent on key attribute C. Here in this slide, both tables have non-existing transitive dependencies, therefore they can satisfy the conditions for 3NF, thus no conversions are needed for both tables. For example, in the users table, both the username and email depend only on the user ID, the primary key. The same applies to the playlist table. That means both are already in 3NF. In this slide, transitive dependency exists between album and artist and genre information. Album name, artist name, and genre are all dependent onto the song title attribute, which is a non-key attribute that depends on the primary key song ID. In the songs table, we encounter transitive dependencies among album, artist, and genre. These details all rely indirectly on song title, which itself depends on song ID.
And here are the transitive dependencies within the songs table. To fix this issue and achieve 3NF, we separate album, artist, and genre into their own independent tables. So instead of having everything inside the songs table, we now have songs table that keeps song ID, song title, duration, and references to artist ID and genre ID as foreign keys. Meanwhile, in the artist table,
it stores artist ID and artist name. In the albums table, it stores album ID and album name. And lastly, the genre table stores genre ID and genre name. By doing this, we eliminate the transitive dependencies. Songs are directly linked to their artist and genre using IDs, ensuring the design is cleaner and free from anomalies.
Now let's talk about the anomalies that are solved by moving from 2NF to 3NF. Anomalies removed in insertion anomalies. When a song that doesn't belong to any album is added to the table, the album column is left empty. But on 3NF, a song details can be inserted independently with artist ID linked as foreign key. A new album cannot be added without a song in 2NF. In 3NF, albums exist independently. In 2NF, an artist can't be added until a song exists. In 3NF, artists exist independently. A genre cannot be added in 2NF until assigned to a song. In 3NF, genres can exist independently. In 2NF, we can insert a new artist, album, or genre unless a song exists. But in 3NF, these entities exist independently, so we can add them even without songs. Now, in update anomalies. Renaming the following attributes requires multiple row updates in 2NF. In 3NF, these attributes are only stored once, thus only updated once. In 2NF, updating something like an artist's name requires modifying multiple rows. In 3NF, we only need to update one row in the artist table. Deletion anomaly. When a song information is removed from the table, album, artist, and genre details will also be deleted from the table. In 3NF, album, artist, and genre are all independently separated and will not be affected when a song is removed. In 2NF, deleting a song could accidentally remove its artist, album, or genre details. But in 3NF, those details remain safe in their own tables, even if all songs are deleted.
Another important refinement involves the song-album relationship. In the 2NF design, album details were stored directly in the songs table, but this caused problems when adding a song that doesn't belong to any album. The album column would be left empty. But in 3NF, album information was separated because when a song that doesn't belong in an album is added, it creates an update anomaly. To fix this, we created a new song-album table. This table links songs and album through their IDs, making the relationship flexible. Now, songs can exist with or without albums, and albums can exist independently. This change also solves anomalies. For example, in 3NF, deleting a song won't delete the album record. Only the link between them is removed. When a song that doesn't belong to any album is added to the 2NF table, the album column is left empty. But separating the album details into a separate table and using album ID as a foreign key to link to song ID. Linking the album information to song information is now optional, depending on whether the song belongs to an album or not. If all songs are removed, the album details also disappear in 2NF because the full row will be deleted when removing a value from the table. In 3NF, album stays in albums table, and the link between songs and albums will only disappear.
Meanwhile, the playback history table and the playlist song table already satisfied 3NF. They don't have any transitive dependencies, so no changes were needed. At this stage, our database is fully in their normal form. To summarize, the final structure includes users table and playlist table, songs table, artist table, albums table, genres table, and song album table. And last, playlist song table and playback history table. This structure is much more efficient, avoids redundancy, and supports the business rules of a Spotify-like music streaming system.
Finally, let's take a look at the functional dependency diagram that represents our design. User ID determines username and email. User ID represents playlist name and playlist created date. Song ID determines song title, duration, album ID, artist ID, and genre. Album ID represents album name. Artist ID represents artist name. User ID determines song ID, stream date, and like. This diagram confirms that our design meets all requirements of third normal form. In conclusion, by normalizing the Spotify database step by step, we eliminated redundancy, solved anomalies, and created a more structured and reliable schema.